That's why it's so perfect. Where did Tofu go? She's magically disappeared. Stunning. Thank you. Ooh. Okay, I know that we've had so much banter and so much amazing support with the charity. We raised over 23,000 again. What I'll do now is I'll reel us back so that we can just at least learn about the photoelectric effect today, okay? So what I'm gonna kindly ask, if you guys are interested in donating, interrupt ahead, honestly. But let's reel ourselves and I can cover this in 30 minutes if we really, really focus. How's that sound? It's because the physics is the simple stuff and the... Yeah, no, I got the joke only after Hexana, sorry. Good luck, I'm gonna need it, Frederick, to focus. Okay. Photoelectric effect is this event, this thing that happens and comes from the words light and electron. Light electron effect. And it is the thing that is given credit to Einstein. Einstein won his Nobel Prize for it. Usually Einstein is known for his special and general theory of relativity, but this is the shit that actually won him the Nobel Prize. And but he wasn't the first one to actually conceptualize. So the photoelectric effect is the main evidence for quantum theory. It was one of the first things that gave evidence for quantum theory. So Einstein really was one of the OGs. And it proves that light acts as a particle. So before we said light, we said a lot of things. Light is a wave. Light travels in straight lines. And light is also... Now I've said light is a particle. I know. I'm going back on it. We will do a lesson about the wave duality of light one day. But for now... photoelectric effect was basically a proof and a demonstration that light traveled in packets as particles, and we call them photons nowadays. But it wasn't actually Einstein who conceptualized it at first. The first person on record, as far as we know, who conceptualized it was actually Newton. Back in the days, I mean, Einstein put his hands on gravity and light. He literally grabbed Newton by the throat and was like, I'm going to take all your theories and ideas and take them away from you. It was Newton that first proposed quantum theory of light. He called them corpules? I'm trying to remember the word. It's a tough word. I can't remember on top of my head. But he did say they have mass. That was the thing that he did define it at his time. That he thought that they had mass. Is it corpuscules? Oh, fuck's sakes. I'm sorry. You guys can find the word on Google, I promise. But the definition of light is that light are a bunch of photons. And the definition of a photon is discrete parcels? Yeah, parcels of energy. What does discrete mean? In physics. Corpusless. Discrete parcels of energy. Discrete packets of energy, even. What does discrete mean? Bless you. Can be measured. It's like digits. So it can exist only as wholes. W-H-O-L-E. It means that a photon can exist in value, like of whole values. For example, one photon can exist as one photon. It cannot exist as 1.5 or 1.3. You can either have one photon or two photons or three photons or four photons. Does that make sense? We used this word before when we were talking about electrons having charge. Electrons can only have discrete charge. So things can exist as one charge of electron, two charges of electron, three charges of electron, but nothing can exist with 2.5 electrons. You can't have that. So that's what it means when we say it's discrete. The energy of a photon, the energy a photon has, is described as E is equal to hf. Oh, we've seen F today. We did the Doppler effect today. What does F stand for, chat? We did it today in Doppler effect. Frequency. Well done. Not farts. Good point as well. Frequency. Exactly. And H is a wonderful scientist, but it's a constant value called Planck's constant. It's a number that exists in the realm of quantum theory, and you cannot avoid it. It's like trying to avoid pi in physics. You're just not getting rid of it. You might as well get used to it. Planck's constant, if you want a number value to associated with it, is that it's 6.63 by 10 to the minus 34 joule second. Okay? A photon goes through the airport security. Agent stops the photon and asks, why don't you have any luggage? The photon responds, I'm traveling light. Now, remember when we were talking about bonds earlier? We were talking about ionic and covalent bonds about a month ago. I don't know if you guys remember that. And remember we talked a little bit about metallic bonds. What's a metallic bond, chat? I know, I'm sorry. Keep the maths and the physics memes coming. We need the physics jokes. A bond between metals. Okay, you're not wrong. Jokes aside, you're not wrong. Oh, you bastard. It was so pretty in yellow. It's because I have a dark mode on. Electrons floating freely among... That's a very nice description. So it is a lattice. The definition, I would say, it is a lattice of ions with delocalized electrons. It's a very fancy word. But basically it means that their electrons are ready to jump ship. In a metallic bond, the metal atoms beside each other are all connected, right? And they kind of not quite share. There's a word that we're not carefully using too much. But there's electrons ready to jump on ship to the next atom. And that electron is ready to jump onto the next electron. And it's basically how current works. This is how current goes through wires. Because the electrons are so ready to jump ship. They're ready to abandon the atom that they're originally associated with. That's kind of a way of thinking about bonds in that way. So let's say we have a metal here. What happens is when we shine a light, light is a form of energy. When we shine a light on the surface of a metal, electrons get pewed off. They go pew! Pew! They flick off the surface of the metal when you shine a light. Basically, you're giving energy to the electrons to jump ship. This makes sense with the wave theory of light, right? You give energy to light. Now, there is a little correction, and I have a note here. If wave theory was the only correct theory of light, then electrons should be liberated with any frequency of light as long as it's bright enough. Hey, what did I just say? Light is a spectrum, right? You can have different wavelengths and different frequencies. And what we're saying is as long as your source is bright enough, i.e. has enough energy, right? As long as your light source is bright, like blinding light, it doesn't matter what frequency your light is, it should be able to yeet off the electrons. This is based on the theory that light is a wave. But dun dun dun! That's not what happens. It doesn't matter how bright the fucking light is. If it's not a certain value of frequency, no shit happens. Like, nothing happens. It is dependent on frequency. And this was weird. Well, not weird. It was actually 100%. What? I know, right? Oh, wrong overlay. There we go. I know that to many people it was like, okay, so what? But from a fundamental physics perspective, like from a classical physics outlook, this was wild. This was truly actually like OMG moment when they found out. So it's just crazy. It's like, well, we know what energy is. The brighter the light source, the more energy you're giving. So no matter how much like energy you're shoving into the electron, it's just not like yeeting off. It's like, what the hell? Like, this doesn't make any sense. What's going on here? I'm getting a bit excited here. I'm not going to go through the full theory because we are running out of time, but I'll just explain it a little bit. It's as crazy as when we found the world round, yeah. I wanted to go through the experimental procedure, but I won't do that today because time is of the essence a little bit. Why no yeet? Exactly. No, we don't care about reflectiveness in this case, Whisper. It is something to consider, but in this case, we don't care about that. So, what actually happens is, if we plot energy against frequency, I'm just giving you a diagrammatic representation of what happens. E is energy max, like the maximum energy that an electron can have. You might sit there and ask, what does that mean? Don't worry about it. Don't worry about it for now. It's not too like it makes so much more sense if I go through the experiment. But like I said, time is a little bit of the essence right now. Maybe I can go back. Let me get this done, and then maybe I can go back and explain the experiment. So we have frequency here. And we have energy max here. So what happens is as we increase the frequency of the light, not the brightness, not the intensity, chat, not the energy of the light, just its frequency. This is wild, right? As we increase it, nothing happens. No electrons get yeeted off. It's just a straight line. Straight line, straight line, straight line. And then out of nowhere, get a straight line. So this, I don't know why I'm getting all worked up here, but I hope you guys take me seriously while I'm cosplayed as Einstein as well. This is serious science. I'm not joking. It's the oh, I think so. I think so, Whisper. I'm happy to be corrected. What we call this is the frequency threshold. F0. That's F0, not F0. So I know we did the Doppler effect earlier and we talked about the observer. This is not observer, this is 0, not O. Frequency threshold. So this is the minimum frequency required. It doesn't matter how bright your light source is. It's the minimum frequency required to yeet electrons off the surface of the metal. This was crazy. So the rest of this energy is given off as kinetic energy. So as the frequency increases, the electron has more kinetic energy. Do you guys remember what the equation for kinetic energy is on top of your heads, chat? Anyone remember classical mechanics? 3 is equal to 3. Half mv squared. Well done. You guys are good. Half mv squared. We don't really need it right now, but. Now, if we plot backwards here, plot the straight line, okay? We hit a negative energy value here. And if we measure this energy, this y-axis here, this is the energy needed to yeet electron. This is what this energy, this y-axis represents. From here to 0, this is the energy that is required to yeet an electron. Okay? So right now, I've just shown you a straight line through the graph. Does anyone know what the general equation for a straight line is? Not a wobbly line, not a squiggly line, for a straight line. Some maths people might remember this as well if you guys have done maths. Y is equal to ax plus c. There we go. So I use y is equal to mx. That's what I say. So yeah, it's interesting to see. Some of you use different symbols. So my symboling that I use, it's correct. The same as yours, guys. But we just use different letters. Y is equal to mx plus c. Sorry, slow chat. No worries, no worries. Sometimes, you know, I phrase things in a certain way and you might think of it in one way. So y is equal to mx plus c. Let's sub in our parameters in here. Y is equal to the energy max. That's just the y-axis, right? The slope, when we we figure out, is Planck's constant. X-axis is the frequency. And the constant, the value that crosses the axis, is this value here, this negative E. I'm going to give it a new symbol. I'm going to call it phi. Does anyone know what phi represents in the photoelectric effect equation? What does phi mean? Has anyone heard it before? Does it sound familiar? Sorry, could you repeat what the frequency threshold is? No problem. I'll go over it now. Fine looking particles. We call it the work function. Has anyone heard that before? Is that a familiar word to anyone? I think it's called the work function. Yeah. The work function. And this is different for every metal. It'll be a different value for copper. It'll be a different value for iron. It'll be a different value for titanium. Every single metal is going to have a different value of work function. First time for me. No worries, no worries. So someone just asked me to explain what fundamental, what the frequency threshold is again. So when we plot the energy of your light source against the frequency, okay, on the surface of the metal, what happens is we're shining a light on the metal. Where is the graph? We're shining a light on the metal, okay? And we turn up our light brighter and brighter and brighter. We're giving it more and more and more energy. And no matter how much energy we give, electrons are not being yeeted off the surface of the metal. No matter how much energy we give. It's like, what the hell's going on? So, but if you adjust the frequency of the source of light, you increase it bit by bit. You increase it here, nothing happens. Increase it here, nothing happens. Sorry. Increase it here, nothing happens. And you just increase it bit by bit by bit. And then, boom! Out of nowhere, electrons start yeeting off. And they yeet off faster the higher the frequency goes. Does that make sense? Does that answer your question? So this frequency threshold here, this value here, is the minimum value of frequency for electrons to yeet off the surface of the metal. Before that, any other value of frequency, it doesn't matter how much energy you're putting into that light. No electrons are yeeting off. They're staying stationary. They're like, bitch, that's not good enough. So they wait until there is a higher value of frequency. It doesn't matter how intense the light source gets. Just not good enough for them. God, they're so picky, aren't they? And so we have now developed, from this graph, we have now developed the photoelectric effect equation, which is really, really cool. Now, let's look at this specific scenario that you just mentioned, Whisper. This moment. The second the frequency threshold is met, that minuscule second is met, in that single moment, what does the equation look like? E max, what value is Y in that moment? What value, sorry, what value is E max? What's the value of the y-axis in this moment here? Zero. Zero. Well done. If any physicist lecturer ever asks you the answer to a question, gamble zero. That's my life advice for you guys. If a lecturer is asking you a question like that, chances are the answer is zero or infinity, one or the other. Thank you, Prema. Welcome in. How are you doing? I appreciate the congratulations for my Nobel Prize win. Okay. Or 42. No, that's only on Tofu Stream. Only on Tofu Stream. So if at that moment, we know that E max is 0. We also know that HF obviously stays the same. But we know that the F is the frequency threshold. So we're just changing F to F naught. That's what that is over here. Plus phi. Rearrange the equation, we find, oh shit, by the way, a small mistake. Very small mistake. It's been minus the whole time. Obviously it's minus, it's negative. Just a small point. Nobody pointed, chat is moving quickly to be fair. Nobody pointed out that it's negative phi. It is negative value, by the way. All of the values up here are positive. All of the values over here are negative. So just in case you don't understand why I have a negative sign here, it's because it's a negative number. Yeah! If anyone in chat had corrected me and I missed it, give yourselves a pat on the back. You're smarter than me. Doesn't say a lot, but you know. So rearranging this equation, F naught is equal to phi over h. So this means, oh, I don't know why I kind of showed this, but it is a really fundamental equation to kind of determine what the fundamental frequency of any, or sorry, what the frequency threshold is of any metal out there. And I'm going to talk about like practical examples about this in a second. No extra credit. Just to point out the elephant in the room, why phi and not a normal letter like Q? Because physicists use Greek letters. We use Greek letters for everything, Baltrazi. We don't, yeah, like it's yeah. Very, very simple answer. We love Greeks. We're infatuated with Greeks. We've been married 3 times with Greeks. Sorry, whisper. It's the energy of the electron. Absorbed, basically. Okay, answer is deal with it. Need more symbols than... Yeah, exactly. You run out of letters very quickly in physics. Obviously, like when... Yeah, like I can't imagine. If we didn't have Greek letters, we would have run out of a lot of symbols in mathematics and physics. So we do need to use Greek letters for substitution. As phi is a unique value, it is... so every single metal has a different value for phi. You're absolutely right. The conclusion from this experiment is that for every electron that gets yeeted off, you have 1 photon. Sorry, probably better to do it the other way. For every 1 photon of a particular value of frequency, it yeets off 1 electron. So the idea behind it is that 1 electron can't absorb 2 photons. It doesn't do that. It's discrete. It will only absorb 1 photon, and only that 1 photon will allow that 1 electron to yeet off. Hello, Tofs. Hello, Mord. Welcome in. How are you doing? And E is theoretical energy needed to yeet 1 energy. So let me show you. E is the kinetic energy of the electron. So that gets yeeted off. So it's 0 here. What does that mean? From here to here, E max is 0. What does that mean? What does that mean when we talk about kinetic energy of electron being 0? I guess like language would be way too common. Yeah, I guess so. Yeah, we do use, yeah. You're basically choosing an alphabet that's the next best thing after Latin. It doesn't move, exactly. It stays in place. Half mv squared. V squared means that it's not moving. So that's basically what's happening here. In these moments, it's not moving. And from here onwards, it moves. The more you increase the frequency, the more it moves. And what is missing in this explanation is that I didn't go over the experiment of how this works. That is something I could go over again, maybe tomorrow in the beginning of class. But I just really don't have time, unfortunately, to go through it. So that's on me. So that lack of explanation is on me for sure. So 1 photon, 1 electron. And this proves that light exists as quanta. It exists as discrete packages. It's a molecule. Okay, molecule is the wrong word, but it was a big revelation at the time, because at the time they thought it was a wave which could exist in any energy value. You know what I mean? It could exist, and it can do whatever you want as long as you provided enough energy for it. It could do whatever it wanted. Do you know what I mean? But this revelation meant that light had to exist as packets. It can only exist in a certain value and a certain amount. And there's nothing you can do to change that. I'm going to say that, and now someone's going to put in, actually, there was an experiment performed. Anyways, that was the revelation that was made by this. And the energy of the photon, what differentiates all photons from other photons, right? There's one photon A, there's another photon B. The difference between them is that their energy can be different depending on the frequency. So you can have a, let me show you a graph. Frequency of light, of EM waves. That's wavelength, frequency. Here we go. Oh, there's a blurry photo.
We have to go back!
We have to go back! Do you guys see this? So depending on your radio waves, infrared, light rays, ultraviolet, X-rays, whatever it is, your frequency is going to be different. And that defines how much energy a photon has. Hold up a second. We studied gamma rays. What do you notice about the frequency of the gamma rays? What do we notice about it? Welcome back for Zerp. Oh, the image is cut off. Okay, sorry. I will move it over here. You guys should be able to see it. Oh wow, this is really cut off actually. You guys might have missed a lot of the board. I'm so sorry. Someone should have said something to me. That I was a papega. You guys know you are allowed to say that I'm a papega. Sorry, let's go back on it. So what do we notice about gamma rays? Their frequency is really high, isn't it? Fucking high as fuck. In fact, gamma rays have the highest frequency. So they're emitting photons with the highest amount of energy. And gamma rays are that dangerous thing. It's that radiation that causes your atoms in your body to break down and to alter. This is why gamma rays are so dangerous when we talk about different scary stuff that happens. Speaking of Ukraine, of what happened in Chernobyl, that was the thing that was scary. Is there a maximum frequency? Yep, gamma rays. I think there is a maximum. It doesn't go past gamma rays for Zerp. I wish that I could turn me into the Hulk. Is there any correlation with alloys and their constituent elements, e.g. bronze with copper and tin? Sorry for Zerp. What do you mean? Would you rephrase that? Oh, sorry, not for Zerp. Zir. My bad. Zir. So, that is the explanation of Einstein's photoelectric effect. I am missing one thing here. I am missing the experiment. And to be honest, I can actually go through it. I have time. Give me 2 minutes. I know you guys are like very, very kind, and I've been streaming for a long time, but I just want to show you the experiment. It's actually not too bad. Let's say you have an ammeter here. This is an ammeter. We have I don't know what this is. It's like a vacuum kind of chamber, and it has to be a vacuum because you don't want molecules in the way of the electrons. And you shine a light on this plate here. Okay, shine a light, and your electrons are yeeted off. What happens if electrons are moving from here to here? What happens to this whole system? So if the copper has 5 value of A and 10 to B, would the bronze have a value to both of it? I don't know, actually. Logically, you'd feel it would be in ratio, but it could be like a weird alloy combination that it would change 0. I actually don't know, genuinely. There is a current. That is right. You will have a current. Electrons will go this way, and you have a current. It becomes a circuit. Now, let's put in a battery. Which way do I want to put the battery? I want to put a battery this way. Let's put in a battery into our circuit, okay? So this is a plus side, so this is the negative side. And what you're going to do to your battery is, as you're shining a light in this vacuum chamber, you're going to increase the voltage until no electrons are passed through. What you're basically doing is you're putting in a force to stop the electrons from bouncing, because this is the negative side. Electrons are repulsed, likes and likes repel. So there's like a counter force this way, while the electrons are trying to go this way. And you're tuning the battery perfectly until no electrons are jumping to the other side. Okay? So at the point, that is called the stopping voltage, VS. You know what your voltage is to stop electrons from bouncing at that moment, at that certain frequency, at that certain value. A bit of equations. Voltage is equal to energy divided by charge. What is energy? We talked about it, kinetic energy. Do you guys remember? Kinetic energy is V is equal to half mv squared. Overcharge? Do I keep overcharge? Oh, charge of a... So we're talking about one particle. What's the charge of one particle? What are the particles that are jumping here? Electrons, right? You can look it up. But I can just put in one electron. It's the charge of one electron. You can also just say that it's the kinetic energy. And so, the equation becomes the kinetic energy of the electron is basically the electron's charge times its stopping voltage. You can actually measure the energy of your electron. And that's how you can plot it here. This is how it's done experimentally. You are measuring the resistance of that electron. 1.6 by 10 to the minus 19 coulombs. You got the number right, real heart. But the unit was just a tad bit off. Well done, though. So this is how it's shown experimentally. You can practice. You can do this graph experimentally. Does that make sense? How it was shown and demonstrated? I should have done this first before I got to everything and did this here. Obviously, I should have shown the experiment first before we got to this part, but I did go back on it. What sort of gas was used? No gas. It has to be a vacuum, Whisper. Why do you think it has to be a vacuum? in this chamber? Why do I want this to be a vacuum? I'm not trying to be a dick. We're probing, we're questioning here. Why would you want it to be a vacuum for electrons to transfer to? So the electrons aren't blocked. Exactly. You don't want to block those electrons from getting to the other side. So you create a vacuum, empty space to let the electrons pass through as easily with no resistance whatsoever. And that is the whole story-ish of the photoelectric effect, which showed that light exists as particles, as quanta, discrete values. I'm contrary. I want to block them. And that is the story of the Doppler effect today and the photoelectric effect. What would happen if you blocked it? You just wouldn't get the right value, Rayhart, and your graph would be off. You'd have error. Because obviously if you're blocking, the electrons aren't getting to the other side, your resistance will be a lot lower. So your graph will be offset. It just won't be true values. You might even not get a straight line. It might look a bit wobbly.